Let's look at the idea of equipotential surface again and its properties. So equipotential surface has to do with, say we have a set of point. If you move around that point, the amount of force will not change. Of course, anywhere else, like over here, the amount of force is different, but here in this case for a point charge, if you move along the same radius in two-dimensional space, in three-dimensional space, again on the same surface, with center being your source charge, what happens? The amount of force will be the same. So this line and surface are your equipotential. They are at equipotential. Now we're looking at the properties. So no work is to be done in moving a test charge over equipotential surface. Yes. So let's prove that. Quite simple proof. So we know that the work that we need to do, right? We can write it as force into displacement, or we can write this as charge into potential difference. So this is nothing but Q naught times of VB minus VA. Agree? So that will be the amount of work that we need to do. That's the whole funda. But VB is equal to VA for an equipotential surface. So we have this entire expression to be 0. That's it. So we don't need to do any work while moving the charges around on equipotential surface. Now, electrical field is normal to the equipotential surface at every point. What it means is, say we have a plane. Of course, it can be curved also. Right? It can be plane also. So what we're trying to tell over here is, okay, if I happen to take up a electrical field, it will be perpendicular to this. Say it's not perpendicular, right? Say it's not perpendicular. Something like this. So that's your direction of electrical field, making an angle of theta, which is non-perpendicular. So it's an angle less than 90 degree, for example. What happens then? Well, we know that using our vectors, vector idea, we can resolve this into two components. Parallel law, triangle law, vector addition, so on and so forth. So this, say, is parallel to your surface. This is perpendicular to your surface. So say I take a charge over here and I want to move it over here. But there is a force acting against that movement, right? Acting opposite to that movement, or in that moment, in that direction itself. But anyways, in this case, it's acting, say, from point A to B, opposite to our movement or charges movement. But there should be no force. There should be no work. If there is a force which is non-zero, then work will be non-zero. But we just prove that work is 0 on equipotential surface. So what is happening over here? Well, what's happening over here is that our assumption of theta being non-90 degree is wrong. Okay, guys. So let me show the write-up. We're using proof by contradiction in this scenario. I hope you guys remember root 2, proving root 2 is irrational and all of that. You studied in your 8th, 9th, 10th grade, somewhere along that line. So let's consider an electrical field that is not perpendicular to the equipotential surface. This implies that there is a non-zero parallel component of the equatorial field. Agree? So when moving a charge on the surface, we have to do work against the electrical field as per this. However, the idea of equipotential surface is that the surface has to be equal potential. So the work has to be equal to 0. Has to be 0. This contradiction arises because of the false assumption that the field is non-perpendicular. So that's how you can write it up. Right? Does it make sense? Quite simple. We have used this in quite a few places. Proof by contradiction. Now, third property is that equipotential surfaces are close together in a region of stronger field and further apart in the region of weaker field. See, again, we have the idea of equipotential surface or electrical field, gravitational field. All of these are fields. They have certain properties that are quite similar, including this. Now, over here, we have a mountain or a hill, and we have somewhere here is a top, right? This space. Now, there are two ways going up the slope. One is this way, one is this way. Or I can tell there are two ways of going down the slope. Actually, there are infinite possibilities, but say we'll consider these two ways. So this is the quickest, and this is slower. Not the slowest, but slower compared to the other one. Now, when we look at the contour map, what can we tell? This set of lines wherein we are moving quicker, the slope is more, right? The slope is more. The lines are denser. Agree? Denser. Here in this space wherein we are moving very slowly, see this diagram is not exact. So here how do I put it across? Here the line density is lesser. Quicker, line density is more. Slower, line density is less. Agree, guys? So keep that in mind. Let's come back to this. So we know that electrical field can be obtained by taking the negative gradient of voltage with respect to distance. How fast the voltage is reducing. In the opposite direction, this will keep increasing. Now, if I rearrange, I'll get something like this. So for equipotential surface, what is happening? Equipotential surface dV is constant. Therefore, dr is proportional to 1 by E. So equipotential surfaces are closer together in a region of stronger field. Does it make sense? If this increases, the distance between the lines will reduce. Does it make sense? So they are inversely proportional. Same as this. The rate at which we are falling, if it's high, the density increases. Means what? The line space, what happens to line space? This implies reduces. That's what denser means, is it not? And here the line space is more. Commonsensical. Right? Does it make sense? Similar to your magnetic field lines, guys. If you have in a closed pack, if you have a lot of magnetic field lines, the strength is more compared to another space, just say neighbor to it, wherein the field lines are less, then the magnetic strength is less over there. We just have a proof for this. That's it. It's not at all complicated. It's the same thing again and again. Whatever you studied in magnetic field, gravitational field, same stuff. And same kind of proof. Just the terms are different. That's it. If you guys want to copy this,